So where we got just before lunch is we now know what a Dirichlet process is. It's a way of generalizing the Dirichlet distribution in such a way that when you draw single points from it, out comes an entire cumulative distribution function. So it's really a proper, it makes sense, it's a legitimate prior on the set of all possible cumulative distribution functions. And if you tried to make it operational from the definition, you'd find it wouldn't be much fun. But a few years after Friedman and Ferguson worked on this stuff, these guys called Sethiraman and Tiwari came up with a quite easy way to sample from a Dirichlet process using a method called stick breaking. So here's the idea. It turns out that any single draw from a Dirichlet process with prior sample size C and prior centering distribution F0 can be thought of as the following. It represents an infinite sum of weighted point masses. And so delta theta j is point mass at a particular point theta j. And the VJs tend to be weights, turn out to be weights. And the way you compute the weights is as follows. The reason it's called a stick breaking algorithm is you take a unit interval and you break it at some random point. Think of it having a stick of length 1, and you break it at some random point called W1. And that's the V1 in this algorithm we're about to look at. Then, having gotten this far reading from left to right, you break it at some other random point, W2, and V2 becomes the size of the distance that you just got from W1 to W2, and so on. And if you do that forever, you will eventually get to 1, and that will tell you that you're done with this infinite sum. But now I have to tell you how the W's are generated. They're IID draws from a beta distribution with parameter 1 and C, where C is the prior sample size. And then I have to tell you where the thetas come from. Well, they're IID draws from the base, so-called centering distribution. And then we have point mass at theta j. So to sample from the prior, we simply draw IID points from the base sampling distribution, and then we include them in this mixture here with amount of weight given by these quantities that come from breaking the stick in that fashion. This Wj times the previous 1 minus k's is a way of saying you're always making the size of the sticks depend on, you're always renormalizing each time to what's left over after you've broken off different chunks of the stick. And this particular representation, that F is like a weighted sum of point masses, means for absolutely sure that you can just see that the only kinds of CDFs you can get from a Dirichlet process are discrete distributions because they are weighted point masses. And we already saw that from before also because the CDFs you're going to get from that thing, that picture I drew before, have to be discrete as well, corresponding to every place, every time you cross over a point in the partition set. And so this is often a drawback because you're trying to model continuous data, and here you are using a distribution on the set of all CDFs that puts all its weight on discrete distributions. So you know the basic fact that you can get arbitrarily close to any continuous distribution by taking mixtures of discrete distributions with the right mixing weights. And so we're going to solve this problem. In a way, it's going to be one of these things where it looks like a defect, and actually it's a feature because we're going to be wanting to do some mixture modeling later on anyway. And I'll say right now why. So far, all I've told you is about what happens when F0 is some distribution that's completely known. But later on, when we start fitting these models to actual data, we're going to want to have the centering distribution be for example, a normal distribution with unknown mean and unknown variance. And we're going to have to mix over the fact that we don't know the mu and the sigma squared. And so that's going to force the kind of mixing that we're interested in, which is going to make the resulting draws from the posterior for the Dirichlet process be as close to a continuous story as you may want. That's going to actually work. And so now we need to talk about the effect of C, this parameter C. It acts like a prior sample size. And so it just behaves exactly as you would think. If you write down a Dirichlet process prior with a bigger value of C compared with one that had a smaller one, that's like saying that you're putting more mass in the weighted average between the data and the prior later on. When we start updating with data, you're putting more mass on the prior. And the way to make that work as far as drawing from the prior goes is that each draw, when C gets bigger, each draw has to be around F0, but with a smaller and smaller envelope, uncertainty envelope around it. So that acts like it's saying we have more and more votes. The bigger I make C, the more the draws out of the Dirichlet process are going to look just like the base sampling distribution, the prior estimate F0. And that's because when you write the way the way the Dirichlet distribution works, for any member of that partition I showed you before, the variance of how much mass the F that you draw from the Dirichlet process places on that set A behaves like the amount of mass that the centering distribution places on that set A times 1 minus that over C plus 1. And clearly, if we make C get bigger, that's going to make the variability around F0 get smaller, because this expression would go to 0 as C got bigger. So this has all been quite abstract. I wrote some R code to implement this for us. I have a function called rdir.lognormal, and it's going to center things around the log normal distribution. And so let me go ahead and kill out of there and get to the course web page where we have some new R code. So under the section about R code, we have something called Bayesian unparametric modeling R code part 1 Dirichlet process DP priors. So I'll go ahead and save that onto my desktop as that code right there. Oh, looks like I already did it. No harm in writing it out again. And now let's run this code with a new copy of R. So I'll go ahead and kill this old one off and start a new one and see what happens. Because I was interested in the log normal distribution, I decided to center things around the log normal here. Let's see if this is the guy I want. Nope, that's the other one. So where did it go? Maybe it's this guy here. Okay, good. So I wanted to write a function in which I input the number C that stands for the prior sample size in the notation I used before. But as you know, when you get into R and type C, it already has a name. C is an important simple function that you know serves to collect the scalars together to make a vector. So I called it CC instead of C in order to keep from getting confused with the built-in function. And I need to tell you one more thing about how that stick breaking thing works. I should have said it before, so let me go ahead and say it now. Obviously, if you're going to rely on a characterization of the Dirichlet process like this stick breaking thing, you can't realistically have something like an infinity sitting around in your computer work, because you can't actually take an infinite number of terms to add together in this way. So what people do in practice is they choose a number, let's call it capital M, that stands for enough terms in the series so that everything is adding up as close to 1 as you want when you look at the entire mass that the CDF results in. So I have to tell I'm going to use lowercase m, I think, in the code. I'm going to have to tell my code what I want to use for lowercase m. And that's basically saying that we're going to take this infinite sum and truncate it at a particular point. This sum has the property that every successive term, 1 by 1 by 1, gets smaller than the previous ones because of the nature of the stick breaking, right? Because the stick is getting smaller. So I add up the sum of the VJs so far, and that's supposed to add up to 1 eventually. And so I look at the running sum of the VJs as j runs from 1 to the number of little m I'm working with. And when that sum approaches 1, I know that the little m I'm working with is large enough. So that's going to be something we need to keep track of in the actual coding. And so I have to tell it how far out to go in the sum that corresponds to the stick breaking thing and what the prior sample size is. Ordinarily, of course, I would have to tell it what the centering distribution is, but I'm going to center it on the log normal distribution. You see right there. So let me go ahead and load the code and run it a bit, and I'll show you what happens when you experiment around with different values of C. So let's go ahead and get, oops, careful. So first I wrote the function rdir, and it just implements the stick breaking thing that I told you about. Then I wrote a function called rdir.fstar, and this function, so the function rdir.ln samples from the DP prior with a particular choice of C, centered at the standard log normal distribution, and truncating the infinite sum in the stick breaking algorithm to little m terms. So, okay, good. So I'll load in that first function. That samples from the prior, and then we need to know how to sample from the posterior also. And so this second function, rdir.fstar, samples from the DP posterior, arrived at by starting with a data vector y, actually starting with the DP prior, with the exact DP prior I had a minute ago, and updating that according to a data vector y. And the result, as we saw by conjugacy, is going to be another DP posterior. So I'll load both of those functions into my current R, and then I'll go ahead and run the code. And this first time, I'm going to run the code with C equals 1 to show you what happens. So let's go ahead and run it. And each of those things, instead of plotting things on the CDF scale, because most human beings don't look at uncertainty on the CDF scale, we look at things on the density scale, I plotted the centering distribution, the standard normal, in solid black line for what's going on the log y scale. So in other words, the logarithm of the y values is standard normal, like we know for the standard log normal distribution. And then every single sample from that distribution corresponds to one of these densities with the dotted lines. And that just looks like chaos, right? It looks like sampling, it looks like sort of raindrops falling on a hot griddle and bouncing back up or something like that. So that seems quite strange, but it corresponds to telling the Dirichlet process prior that we don't have much weight on the standard normal. We used a small value of C, like 1, and the result was that. So like it says here, and it also printed out some numbers, all those different stick breaking sums for all the iterations that I asked it to do. And you see all the stick breaking sums turned out to be 1 with the value of m that I'm using here. So I made a note to myself, the numerical output is the stick breaking sums with the value of m used. If they're not all close to 1, that value of m is big enough, and otherwise you need to make the m bigger. So you can see that with this small c value, the prior is not being guided much on any single draw by the centering distribution. Let's look at it again. It sure looks like each of those draws has nothing to do with the standard normal. And yet, I wish I'd wrote the code and showed you, if you were to average all those densities, you would discover they average out almost perfectly to the standard normal. So even though each one of them is very noisy, they are being disciplined by the standard normal in the sense that if you get lots of them and average them, you get back the centering distribution that you started with. So now let's crank it up a little higher with C equals 5. What do you expect to happen now to this picture here when I crank up C from 1 to 5? It acts like a prior sample size, and so what should start to happen to those dotted line densities? We're centering things around the standard normal, and we're giving previously, with this picture here, you're seeing we're only giving 1 vote in the prior, so to speak, to the prior centering distribution. As I give it more votes, then what should the draws from the prior look like? They should be still guided by the normal 0, 1, but in what way? Even more chaotic than this or less chaotic? It should be less chaotic, right? Because we're giving it a bigger sample size, a bigger prior sample size. So let's run the code now with C equals 5 and see what we get. In fact, maybe it'll be a little bit less chaotic if I reduce the number of repetitions from 50 to 25, we'll be able to see what's going on a little better because they write over top of each other so much. And now all the stick-breaking sums are still 1. And check it out. It's just what we thought. With a bigger value of C, we're still being guided by the standard normal, and you can kind of see the nature of the guidance now a little bit better. Literally, with your mind's eye, if you imagined averaging over those densities, it would pretty well track that nice thick normal curve pretty well. Now let's crank it up to C equals 10, and the result should be what? Even closer to that. So let's go ahead. Let's see. Actually, I cranked it all the way up to 20 next. So like it says here, the draws from the prior that we just saw are now being gently pulled toward the centering distribution. Let's do it over again now with C equals 20. And again, I'll do 25 repetitions to make the picture a little bit less chaotic. Now the sums aren't 1 anymore, but they're still respectively close to 1. And so now we start seeing that with C equals 20, the draws are really looking a lot like each CDF that's being pulled out when converted to a density is looking quite a lot like the standard normal density, which is just what we wanted. So like it says here in the comments, now the influence of the centering distribution is strong. Let's run the code over again with C equals 100 now. And again, I'll stick to only 25 draws from the prior. And now pretty much every draw should look quite a lot like the standard normal, except we're not allowed to look at them yet because look, all the cumulative sums from the stick breaking are only adding up to some number around 0.6. And so that means that we don't have enough terms in the finite sum that approximates the infinite sum. So I was using, looks like when I called rdir, I was using 100 terms in the finite sum. So let's crank the m up to 500 this time and see if that's going to make for better sums. So I'll put this back to 50, or rather 25 repetitions so we can see what's going on a little better, and run the code now. And now with 500 terms, all the partial sums are really close to 1, and I can look at the picture and have it be valid. And check it out. With rare exceptions, every single draw is looking almost exactly like the standard normal. So when you put the C value big enough, the prior is starting to shout, this data comes from a standard normal distribution. Whereas before, when C was 1, it whispers, this data may come from a standard normal distribution. So this provides us with the tuning constant that we need. There's actually 2 tuning constants in this thing, the prior centering distribution and the prior sample size. And they behave just the way you would want them to. So like it says here, this is almost but not quite like putting point mass on the standard log normal distribution. In other words, that's almost but not quite like fitting a Bayesian parametric model in which you pretend somehow you knew the data were IID from the standard log normal distribution. And that is what, of course, would happen in the limit as you made C bigger and bigger. All the draws would tend to perfectly coincide with the standard normal with no uncertainty at all. Now let's look at some updating with the Dirichlet process. So this code generates a data set with 100 observations and a long right-hand tail, even on the log scale. So I'll show you that by plotting the histogram for you. All I did was I took log normal values and added 1 to them. And so that's going to be long right-hand tail a little bit away from 1. And so there's our, away from 0, I mean. There's our data set that we're going to try to learn from. So now I'm going to run the function that does prior to posterior updating within the Dirichlet process family. I'm still going to center things at the standard normal, but then I'm going to vary the value of C. And this is a data set with n equals 100 observations. And so now we really can begin to use that terminology correctly that I've been incorrectly or loosely using a minute ago about votes. C literally acts something quite a lot like how many votes in the compromise. We're going to be having C votes from the centering distribution and N votes from the empirical CDF. So let's see how it goes. So this code right here samples from, and I'll again set it back to 25 so we can see things a little better. It samples from the DP posterior obtained by A, starting with the DP prior, centered at the standard log normal distribution with C equals 1 to begin with. And then B, updating that prior in light of the data set Y with M equals 150 terms in the stick breaking sum. So let's try it. So all the sums work fine. And what you see is happening is that with C of only 1 and N of 100, all of the draws are being guided by the data, but because C was only 1, they have a lot of variability, and also because N was only 100, they have a lot of variability. What will happen as we start making C larger? The posterior distribution will start to shift away from the what toward the what, away from the data toward the prior. That's right. So let's try it. Let's repeat that same code with C equals 50. And I'll again show us only 25 of these guys. And I run them. And I find out that actually the sums aren't really adding up yet. So let's run it over again with a bigger value of M. So I've got currently an M of 150 right there. So I'll put in 250. Now my partial sums are close to 1, and I can begin to check it out. And look what's starting to happen. Now that C is on the order of, what did I put it up to this time? I put it up to 50. Now that C is up to 50, the draws are becoming more concentrated because C is bigger now. And also, they're becoming more like a compromise. Can you see between the data in blue and the prior in black? They used to be all over there in the world of the data, and now they're moving toward the prior. And now let's run it over again with C equals 250. What do you expect to happen now? Compared with this picture, with C run up from 50 to 250, what do we expect to see? It'll move even farther toward the prior, and away. It'll abandon the data even more and move toward the prior. Pardon? Yeah, what's going to happen is, again, I don't have enough. You can see what happens as C gets bigger. You need more terms in the partial sum, and so going back to my code here, I said again I need a bigger value of M. I'll try 500 this time, but you remember C is quite large this time as well. I think I'm going to use 25 draws this time again, and this is something that you need to get practice with. And also with better code, we're still not up at +1. With better code, I could simply not even input an M. I could ask my code to keep calculating partial sums until they get up to +0.99 and stop, for example. That would have been smarter code, but I didn't code that in. So let's go back one more time and try. Probably 5,000 is more than we need. Let's try 1,000. Well, let's try 5,000. It's going to take it long enough to run now that we might actually be able to watch the individual samples appear like a movie. So let's see if we can do that. So now look, the actual draws are appearing like draws like a movie. Not a very interesting movie, I'm afraid, but it's a movie. And we see things moving even farther toward let's see. Look, it's still at 250 that's why. It didn't move very far because I left the C mistakenly in the code to 250. So let's try 500. I can see that I need to edit this particular page on this particular file on our course web page to now by the time we have C up to around 500, almost every single draw is trying really hard to be just like the standard normal. It's shifted slightly toward the data because all those curves are a little lower than the standard normal, moving a little bit toward the right. But so you get the flavor of it. David Friedman actually succeeded with this idea. He created a prior on the set of all possible CDFs, which is like putting a prior on the set of all possible densities or probability mass functions. It has the property that it's user-friendly. You get two things to tune for yourself. One is the centering distribution in the prior, and the other one is the number C that acts something like a prior sample size. Cool. But there's more. So now I showed you the code. Here's the code, blah, blah, blah. And then I showed these pictures. And so you can see this is static versions of the pictures I just showed you. And so with C equals 5, quite a lot of dancing around. With C equals 50, not much dancing at all. Now, from the updating I showed you before, let's go back at equation 8. Why was it equation 8? No, equation 8 is wrong. That should be equation 9. Look what this says to do. Every time I take a draw to construct the data points that go into the F that becomes a draw from the posterior, literally what I'm doing here is I could choose, with probability C over C plus N, I could choose a point from the centering distribution. And with probability N over C plus N, I could choose a point from the empirical CDF at random in an IID fashion. And that would create a sample of points which, when taken together, would have the empirical CDF that would match the posterior draw that I'm interested in right here. So David Friedman didn't notice this, I'm quite sure, because we talked about this once and he mentioned that he never saw it. But look what this is doing. Suppose C were 0. Then how would I simulate the data points that would make up a draw from F? It's the bootstrap. So the Dirichlet process is a generalized version of the bootstrap, in which the way you build up the samples that create the sample version of the draws from the prior or the posterior is like a bootstrap, except a certain percentage of the time you make an IID draw from the empirical CDF, which is like making a bootstrap draw from the data, and the other part of the time you make an IID draw from the centering distribution. So if Efren had known about the Dirichlet process in 1963, he could have invented the bootstrap in 1963 by just looking at this equation here and saying, oh, something pretty interesting happens when I set C equal to 0. I get a new way to think about things. I sample directly from the empirical CDF and see what I get. And oh, my goodness, there's the bootstrap. So from equation 9, it should say on this page here, I'm now on page 17 of part 6, section 1. Sampling draws from F star with Dirichlet process priors is easy. Generate a uniform number, and then sample from F0 if that uniform number is less than or equal to C over C plus N, and from the empirical CDF otherwise. That gets you the right proportions. This is clearly a direct generalization of the bootstrap. When C equals 0, you sample entirely from the empirical CDF, which is the bootstrap. But when C is greater than 0, the tail weight and skewness information can come in from the prior centering distribution. So this is a way to solve the problem I showed you before. Remember how we had this problem where the bootstrap was unable to deal with the log normal story with small samples because it didn't know anything about the tail beyond there. So if we do generalization of the bootstrap, where sometimes we resample from the data and other times we sample from the centering distribution, then some of the sample draws in that part of things will fall out in the tail farther than the biggest observation will, and we'll get a better idea what's going on. So that's a way that you could think of using the Bayesian nonparametrics to broaden the scope of what we would do parametrically on the one hand, and also broaden the scope of what we would do from the bootstrap by itself. So now, to simulate from the posterior distribution, just repeatedly draw F star from this particular weighted average Dirichlet process and then calculate the variance. So C, you can see, acts like a tuning constant. Successful nonparametric intervals for the thing we care about, namely the variance functional. So this is the variance functional that I was interested in before. And in creating nonparametric intervals for this thing will result, I'll get good ones, if I can choose a compromise C that leads to well-calibrated intervals across broad ranges of underlying F. And the rest of this thing shows what happened when my master student and I tried this idea out on various possible data generating situations. And I'm not going to I'm not going to focus on it too much here. You can indeed, oh, I'm sorry. You can indeed arrive at compromised values of C that work across quite large different, quite different data generating distributions. So basically, this at the bottom, page 17, that I said out loud, is saying again here on the page that C acts like a tuning constant. And so when I'm trying to get successful Bayesian nonparametric intervals for the variance of the log normal distribution, I can choose a compromise C that works really well at the log normal, and it also works at other underlying Fs. And so there's some tables that show that my student and I showed that it's possible to come up with compromise cheating, rather compromise choices of C. But this table that I showed you is still cheating because I'm using the standard log normal distribution, and of course the mean and the variance of the data generating distributions, I picked them in a way that was chosen to match those of this standard thing to avoid having to wonder about what the location and scale are. And so the solution, which will move us in the direction of Dirichlet process mixture models, and will also remedy the problem of the Dirichlet process always producing draws that live on discrete distributions, is just like this. This is equation 12 on page 19 of part 6, section 1. It says, well, first of all, take your y's and take their logarithm, and let's call those numbers zi. And now we write down De Finetti's usual model that if you knew what f was, zi given f would be id from f. And now I put a prior. I put a Dirichlet process prior on capital F with values c and f0. And now, instead of centering f0 right exactly at the standard normal distribution, which is the right thing on the log scale, that's really what was going on, I now have the freedom to center it at not just a single distribution, but at a whole family of distributions. So this is extremely cool. This is a way to say to the Bayesian nonparametric machinery, please tell me about the thing I care about, but if I'm wrong about the sampling distribution being normal with unknown mean and variance, please figure that out for me. Work out what the actual empirical distribution is, and shift the mass in posterior space about the CDF, shift it away from the incorrect normal and toward what was really going on. So I can really eat my cake and have it too here. I can learn about the mu and the sigma squared, and also about anything else on the scale of the z's that I care about. And also the posterior, if the data really aren't normal to begin with, the posterior will adapt smoothly toward whatever the real data generating mechanism is. It's an extremely cool idea. Now, there are some implementation questions that you should be having in your mind. First of all, this can't be fit by any simple Monte Carlo like I just showed you. It has to be fit by MCMC. And next time I will be bringing to you functions from the CRAN library that do this Bayesian nonparametric fitting with Dirichlet process mixture models. This one's called a DP mixture model because we're mixing individual Dirichlet processes across our uncertainty about mu and sigma squared. And that, as I said, serves the dual function of picking up our uncertainty about location and scale on the one hand, and also of mixing across discrete things with a really continuous story for mu and sigma squared, which is going to make the posterior for f be very, very close to continuous. So that's going to be great. So one thing is, how do you do the MCMC? And my answer next week is going to be, you use functions from CRAN. You don't have to write this code yourself anymore. You use functions from CRAN. Here's another implementation question. How long do the functions from CRAN take to run in real clock time? And the answer is going to be longer than you would like, because if you had pretended that you knew that the data really were log normal, you know what, from our example so far with WinBugs and RJAGs, this model would fit in a very zippy fashion, right? This is one of these models where if I pretended I knew things were log normal, I could just go right in, and you remember that little counter in WinBugs that shows how many iterations? It will do 100,000 iterations and say 100,000 iterations in 0 seconds. But if you now expand the horizon and allow the model to say, gee, I don't know if things really are normal or not, and I'd have to try to learn the underlying CDF from the data, then you can imagine that it's going to take a lot longer in MCMC time to get a good idea what's going on. And the reason is that your uncertainty in capital F is going to turn out to be intermingled with your uncertainty in mu, for example. And therefore, having to learn F is going to bleed over into extra uncertainty about mu. And the result will be that, yes, we will get time series output for mu and for sigma squared and for other things we want to monitor. But the time series output will no longer look so nice as a quick time series, one that's close to IID white noise, for instance, or maybe even is IID white noise. What it's going to look like is autoregressive processes of order 1 with a really big autoregressive, with first order autocorrelation, bigger than I've ever shown you before. So one practical question you might have, as I just said, is how long is the MCMC going to take? And the answer is longer than we would like, especially when little n is large, because we have to learn an entire CDF over a very broad region, and this algorithm doesn't scale that well with n, with sample size. And the other practical question that you would want to have probably is, how do I pick that number c? And in particular, now that we're trying to update to a posterior on capital F using n data points, the question now becomes, what is the right relationship between c and n, so that if I put in an F0 that's not very close to the true data generating distribution, I will be able to recover from that mistake and get good answers. Because you saw how it works. The posterior Dirichlet process is going to be centered at something which is a weighted average of the F0 and the empirical CDF, with weights given by C in the case of the prior and N in the case of the data. What if I make the C really large, and yet the F0 is nowhere near the right answer? Then will the Bayesian nonparametric machinery be able to recover from that? Answer, no. It'll produce a posterior that's still highly tilted toward the prior, and the prior was wrong as a centering distribution. So this question I'm raising right now is one that no one has yet answered satisfactorily in the literature. I'm working on it right now toward writing a paper about it. Basically, it's a practical question. As a practical person trying to use this as a black box for making good predictions and learning about the world, how do I pick that number C, and how do I pick the F0 so that even if F0 is fairly wrong, I have a decent chance of recovering from that with this BNP machinery, Bayesian nonparametric machinery? And does that value of C depend upon N? Well, yes. And how does it depend upon N? Well, no one knows yet. That's what my student and I are working on. Now, let's talk for a little while about the other way to do Bayesian nonparametric fitting. This is a method called Polya trees. And I have another case study for us here. It's a topic in risk assessment in nuclear waste disposal. It also turns out to be something that would involve a parametric model that's log normal. But as we've seen in this example I showed you a minute ago, it would be good if we could, instead of pretending we knew that things were log normal, write down a Bayesian nonparametric prior that centers things at the log normal. The data that I'm going to show you, and again, I didn't bring that data set this week, it looks like, but I'll bring it next week. Maybe I have it in the other, yeah, let's try that. Forgive me for a moment while I shut this one down and fire up the other one. Let's see, this is 6 part 2. Yeah, so let's see here. Yeah, here it is. One of the things I worked on when I was at the University of Bath in England before coming to Santa Cruz was risk assessment in nuclear waste disposal. And I don't remember if I've ever talked about that case study here so far. Does that ring any bells? How do we dispose of spent fuel rods and things like the suits that those guys wear to keep from getting killed that get radioactive? How do we dispose of that stuff right now? Does anybody know? Think about Fukushima. Actually, no. At Fukushima, they didn't send anywhere else. What they did was they kept it right on site. And in fact, they put it, what you do with the spent fuel rods is you put them in pools of water, and you make sure the water's cool enough that as the heat coming from the radioactivity infuses out from the rods into the pool, things never get so hot that the rods melt. They have to keep the water in this. It's a big swimming pool. They put them in the swimming pool, and no one's allowed to get anywhere near it because it's radiating a lot of radiation, right? Well, what happened at Fukushima is that they put that pool that had the spent fuel rods in it on top of the reactor, on a flat place on top of the reactor. And when the reactor cracked open, the containment, there was no containment thing over top of it, and the pool that was holding the spent fuel rods just broke in half, and all the spent fuel rods fell down inside the reactor. So that was a bad American reactors don't put that pool right on top of the reactor, but there's some place on the site. The answer to my question is, we currently dispose of nuclear waste at the same place it's produced because it's too much of a political hot potato to move it somewhere else. And because that's part one of the problem politically, and the other part of the problem is, where do you move it? Have you heard of the acronym NIMBY? Ever heard that phrase before? It's a British phrase that some people are knowing now in America. What did you say? Not in my backyard. It started in Britain. And the basic idea is, I don't want to be anywhere near that place that they're going to try to dispose of this stuff, right? And so for a long time, no state in America ever wanted to even be the place that would be the proper repository for this stuff. Finally, the government started offering huge monetary incentives to states if they would please do it, and Nevada won. And we actually have a place to do this now. It's called Yucca Mountain. And it's been built at a cost of billions of dollars, and it currently is standing idle because once the Nevadan people decided that they wanted it because they got all this tax benefit from it, when the tax benefit ran out, they decided they didn't want it anymore. And their Congress people succeeded in lobbying the White House to the point where Obama decided not to open this thing. And so it's sitting there ready to use and not open. So we still have our spent fuel rods at all the nuclear power plants around the country, where it would be pretty easy to grab them if you were a terrorist, and also it would be pretty easy for something bad to happen and have them break open and radiate. Okay, so the current system is very unsafe. When I was in England, I worked as part of a multidisciplinary team and also a multi-country team with partners from Italy and Portugal and Spain and Denmark, if I remember correctly. No, it was Sweden. In which we tried to do a better job than anyone had ever done before of assessing the risks of a particular method for disposing of nuclear waste. Namely, what would you do if you were trying to be smart about it? Well, you could put it in a rocket and shoot it into the sun. That would be one thing you could do. And of course, if the rocket got to the sun, would the burst that came by the rocket being absorbed by the sun do any harm to the Earth, do you suppose? It would be like the movement of an eyelash of a gnat, if gnats had eyelashes. Okay, so if it got all the way to the sun, that would be a good way to get rid of the stuff. But what's the downside? Yeah, it might not get there, right? What if the rocket blows up on the launch pad or up in the atmosphere on the way out of the atmosphere? Then essentially we've set off a little nuclear bomb, right? So that's not good. Some other people said, okay, let's bury this stuff way deep under the ocean. But didn't we just have some experience with deep ocean drilling recently? And that didn't work out too well in the Gulf? So that's probably a bad idea. But the burying idea is a good idea. So what about if we do the following? Let's find a geologically stable place. A place that the geologic record shows has not had any big earthquakes for a really long time. And we'll dig a mine shaft there, down pretty far. And at the bottom of the mine shaft, we'll create a containment vessel that has many barriers, many layers of barriers, concrete and lead and all this stuff. And then all we have to do is get the stuff to this place and get it down the shaft and put it on there. And then once the stuff is there, you go back up to the surface and you put a sign on the top of it that metaphorically or actually says, warning to future humans 4,000 years from now, do not mess with this place. There's nasty stuff under there in a language that they will no longer be able to read, right? So there are some downsides to this approach as well. But would you guess, if you did a good job of finding a geologically stable place, and you had a good way that was terrorist-proof, or at least almost nearly terrorist-proof, and also very unlikely for the stuff to crash with terms of rail cars and things like that to get it there, what would you guess would be the order of magnitude of the risk of this new system compared with the current one? Do they sound about equally risky, or is one of them going to be less risky than the other one? In fact, we were able to show that even thinking about the risks of sending the stuff from the nuclear power plants to this place and so on, you put all that stuff in, the new system would be thousands of times less risky than what we have now on a probability scale in terms of probability of something bad happening over a fairly long time horizon. And yet, people who don't like nuclear power, this is another reason why Obama shut this thing down and why the one in Europe hasn't been finished being built yet. People who don't like nuclear power were able to make the following argument. Step one in this argument, your new method of getting rid of the radioactive waste does not have zero risk. Therefore, step two, we should not do it. How do you like that argument? What's wrong with that argument? Zero is not the correct reference point. What's the correct reference point? the risk of the current system, which is thousands of times bigger. And yet the people who don't like nuclear power were allowed to get away with that argument in the public forum. And so that's partly why we're here where we are. So I worked on this team for a couple of years. And like it says back here on page, wherever we are, I guess it's page 2 of section 6, part 6, section 2. At present, this is a little bit more formal than what I just said. Deep geological disposal based on a multi-barrier concept, that's the thing that the bureaucrats write about now, is considered the most promising option. So think about a deep underground chamber. And of course, the safety of this concept relies on the safety of the mechanical and chemical and physical barriers offered by the geological formation itself. And in one part of the work we did, we separated out the risk that came from putting it on trains and trucks and moving it there, and we talked only about what would happen in terms of risk at the site. Well, what could happen? Maybe you were wrong about the geology, and maybe 800 years from now there is a big earthquake right there. Then the containment vessel is going to fracture, and radioactivity is going to start to seep out, and the way it'll do it is that the radionuclides, as they're called, will bind with water molecules, and they will diffuse in cracks in the rock. And so you can use applied mathematical modeling, fluid dynamics based on diffusion processes to predict how fast the radionuclides would migrate from underground to the surface, or at least close enough to the surface for it to contaminate drinking water. And so we built models based upon in which the mean values were predicted by solving systems of partial differential equations numerically to get the mean values. And then because you're uncertain about the inputs to that little PDE solver, the actual tuning constants that drive the partial differential equations, you have all kinds of uncertainties, and so you build a model that's exactly the sort of thing that my department at UCSC was founded to do. Our department's called the Department of Applied Mathematics and Statistics, and we have about half statisticians and half applied mathematicians. So you get people to work in teams where the applied math people do the PDE part of things, and the statisticians do the uncertainty quantification based upon not knowing the inputs and having structural uncertainty about what the right system of PDEs is and things like that. So it's a very nice, and by the way, this is a microcosm of many, many scientific problems these days where the mean surface is driven by an applied math model based upon some sort of diffusion process, some sort of fluid dynamics process, something like that, some process that's unfolding in time and space according to PDEs. Climate modeling, global climate modeling is just like this because getting the mean surface on what is going to happen to temperature and ozone and so on is an enormous PDE solution, a solver kind of problem. Okay, so our goal here is predicting outcomes, including radioactive dose, for people on the Earth's surface as a function of things like time, how far the disposal chamber is underground, and so on. And so there's a agency in Britain that used to be called the Atomic Energy Agency that used to be part of the government, and then it got spun off as what the British call a quango, which is a quasi-non-governmental institution. Did I get all the letters right? Quango, quasi-non-governmental organization, quango. Is that right? Yeah. And so this thing is now partly government and partly private. And they write computer simulation models. My colleagues that I was collaborating with here, they have one called Mascot, and it numerically solves complex systems of partial differential equations. And so you end up with a flow model that looks like this. Mascot takes geosphere inputs, which correspond to uncertainty in the scenario of how the actual accident might occur. And it also takes chemical constants, which serve as parametric uncertainty. And once you put in vectors for each of that chemical constants and the geosphere inputs, it does a deterministic numerical PDE solve inside the black box there. But you have structural uncertainty about what the right set of PDEs is to fully model the physics of what's going on. And if there's anybody in the room who's ever tried to do this, it's a nasty business because you start writing down simple models of diffusion and you realize that they're not complicated enough yet, and you make them more complex, and now that you have a much harder set of PDEs to solve, and you actually have substantial uncertainty about what's the right set of PDEs even to be solving. And then out come predicted outputs, which we can compare with actual outputs if we have any, and thereby we can quantify the other source of uncertainty here. So this little diagram shows 4 potential sources of uncertainty: scenario, structural, parametric, and predictive. Of course, where do the actual outputs come from? We don't really want to do this stuff, right? We actually let the radionuclides go and see what happens, but actually they do. They don't run radionuclide experiments, but they run diffusion experiments like this all the time, where they bury something not very nasty under the ground, and they let it seep, and they actually measure how long it takes for it to get to the surface as a function of how much water pressure there is and stuff like that. So we actually do have actual outputs that we could use to calibrate these models with against data. And also, I don't know if you know it, but in South Africa, there is a uranium mine that is actually serving as a diffusion source for radionuclides. They've been mining uranium out of it for a long time, but it's also the radionuclides are seeping out of the surface of the mine and heading toward the surface. And so we actually have a natural experiment in which we can see how fast these things move. So there is actually some data for what would happen under these conditions. All right, so what people tend to do to quantify parametric uncertainty is they make draws from probability distributions across different plausible inputs for the parameters. And every time you run the PDE with a different set of random input, parametric inputs, you get out a random set of outputs. And so you can study statistically, you can study the mapping from inputs to outputs. Those of you who've done filtering, this thing that's the PDE solver in here is like a big, complicated nonlinear filter. It takes in two inputs, and it filters them nonlinearly into a set of outputs. And what you're essentially trying to do is to reverse engineer that filter and figure out what's going on inside the box as a way of being able to do better predictions. Now, so what we end up with is with different stochastically generated inputs, we do this over again capital N times, and we get capital N dose estimates at each of t time points for each scenario that we're interested in. So let's pick a particular time point to make things simple and a particular scenario. Then we run their program mascot a bunch of times, and out come predicted doses on the surface of the Earth. And even though this distribution, if you think about what it's going to look like, it's going to be very, very heavy-tailed, heavy long right-hand tail, because most of the numbers it's going to produce, unless you have a really catastrophic scenario, most of the numbers it's going to produce are 0. And then every now and then, with small probability, there are going to be some potentially really big doses if something really bad happens. So these distributions are far from Gaussian, and yet the regulatory agencies in Europe and the US insist upon summarizing the dose distribution at a given time point by the mean. So you're trying to learn the mean of a density that has an extraordinarily long right-hand tail. And the number, capital N, of Monte Carlo repetitions that you can make is constrained by time and money. This often has to be done on a supercomputer when the PD systems are big. And so capital N is almost always less than 10,000, and it will often be on the order of 500 to 1,000 points. And so you don't have very much data, and you have a very heavily skewed distribution, which includes probably a lot of zeros and then some numbers, some of which are pretty big, and you're still going to try to learn about the mean of that. To the eBay people in the room, I'll just say that should remind you of a problem that we're thinking about at eBay. But here it is all over there in nuclear waste disposal back in the European project. And as we saw with the log normal story, with relatively small sample size, the concern is that you haven't seen all of the right tail yet in the data. And so maybe we could do something of a Bayesian non-parametric nature to figure out how to do better than what we would get by just trying to fit parametric models. So that was I made progress on that in one of the projects I worked on there. And I'll show you some of those results either today or next time. So here we are back in section 1 of the Bayesian non-parametric stuff, and I'm back to the part where I want to tell you about how polyetries work. So we now have a very long right-hand tail distribution. It's going to be a mixture of a point mass at 0 and then positive values with a highly skewed distribution. And a simple thing to hope that might be true is that the positive part looks a lot like a log normal, a single log normal distribution, even though it might well look like a mixture of log normals. But to make things simple, let's just talk about a single log normal distribution. So now look, a parametric model would just go like this. Take your yi values, hit them with a log, and log yi, I'm on page 20 now of section 1 of part 6. Log yi is modeled as equal to the truth, the mu that we're trying to learn about, plus sigma times a noise term, ei, and mu and sigma squared have a prior, and the ei's are IID from the standard normal distribution. And the reason I separated out the sigma in this way is that it's just another way to write things. I could have said it was log yi's were equal to mu plus ei, where the ei's were IID normal with mean 0 and variance sigma squared, but this is a simple way to do it. It makes the normal 0, 1 cleaner. Okay, so this is a parametric model in which the first line makes good scientific sense, just from measurement, on measurement grounds, and the second line brings in any information you have external to things. And the third line is the one that's suspect from a scientific point of view, because why should this thing be exactly log normal on the raw data scale? In fact, there's no reason why it should be exactly log normal. So the polyetry idea, which we could have solved also with the DP prior, a DP mixture model, where we mix over the uncertainty of the mu and the sigma squared, the polyetry idea is to replace the last line of this set of equations, which expresses certainty about the distribution, namely that we know things are IID normal 0, 1 on the log scale. It replaces it with a distribution on the set of possible distributions for the errors. So just like the DP does, except a different way. And so now the new model looks like the top of page 21. It says the first two lines are identical. And then the next line says, if you knew what capital F was, the EIs would be IID from F. And we're going to always normalize the F's to have mean 0 and standard deviation 1 so that the mu and the sigma have the same meaning across all implementations of this. And then we place our uncertainty about F by putting, instead of a Dirichlet process prior, we put a polyetry prior. And now I want to tell you how that works. And the polyetry prior is indexed with two things, capital pi on the one hand, and script A subscript C. And you remember how the Dirichlet process had two inputs. One was something that was like a prior sample size, and the other was something that acted like a prior estimate of the underlying CDF. The same thing works with polyetries. The pi part of things turns out to be the place that you load in the prior information about the centering distribution. And the script A sub C turns out to be the place where you load in the prior sample size, in particular with that number C in the subscript of script A. So now let me tell you a bit more about that. Because they're called polyetries, you should expect there's a tree around here somewhere, and there is. Capital pi is a binary tree partition of the real line, where epsilon is just a binary sequence of ones and zeros that locates the set that you're thinking about in the tree. And so what you need to imagine to see how a polyetry works is the following. Actually, I can start it on page 8. Suppose we wanted to center the polyetry on the standard normal distribution. Then binary trees, oh, thank you, yes. Then binary trees, of course, have different powers of 2 at each level that corresponds to a layer of the tree. So the top layer, let's start with 2 sets, partition sets, and with the standard normal distribution, so I'm going to center the polyetry at the normal 0, 1, the standard normal distribution. So it's very natural, according to the normal distribution, to center things at 0. And so in the notation I'm using over there in the printed lecture notes, I'm going to call this set here B sub 0 and this one B sub 1, where 0 always stands for going left and 1 always stands for going right when you have a chance. And the image of dropping a pit ball at the top of this thing and having it have to choose between either going left or going right at each level of the tree is a very helpful image, because that's how we're actually going to generate random draws. Now, at the next level down, I bet you can guess that there should be 4 partition sets. So there's 2 to the 1 partition sets here and 2 to the 2 partition sets here. And each one of them has to be a refinement of the previous partition. And so we obviously go like that. And now I want to partition this one into 2 pieces and this one into 2 pieces. And a pretty natural way to do that would be, since we set things up so that the normal had a half of its probability this way and half of its probability this way, why not pick partition points so there's a quarter, a quarter, a quarter, a quarter? Why not? And this set here, using that same notation, is going to be called B01. This one is going to be called B00, because we went left both times. This one's going to be B01. This one's going to be B10, and this one's going to be B11. So do you see the epsilon notation? It's an increasingly long sequence of zeros and ones that tells you whether you go left or right at each level of the hierarchy, at each level of the tree. So where is this place right here? It's the place that under the standard normal curve that has half of its area, rather a quarter of its area to the left of that place. In other words, in the standard normal curve, it's capital phi inverse of 0.25. And that's 0, of course, and which is some number like, I don't know, 0.6 something, I forget. And this is phi inverse of 0.75, which is, this is minus that number, and this is plus, of course, the same number. So it's easy to use the normal curve to work that out. In fact, here it is right here. Q norm of 0.25 turns out to be, yeah, minus 0.67 and plus 0.67. And now, my friends, continue, right? We have an algorithm now for building a tree. The next level down is going to have 2 to the third partition sets, and you go in 8. And in theory, you continue down forever. And when you're done with that, this thing here is called capital pi, that tree right there. And we have, in a certain sense that I'm going to show you after our break, centered the Polya tree at this distribution by having built a tree just like that. So it's time for our next break. Let's stop now and start again at 2:45. And so BC Ops, I'm going to shut things off now, and we'll start once again right at 2:45. Thanks very much. So we were talking about how to build a Polya tree prior, and I've explained what that object pi is in a little diagram for centering things at the standard normal distribution. Returning to my little diagram for a moment before we get back to the PDF. Here's that diagram pi. And now that I've shown you how to do the first and the second layers, you know how to do all the other layers already. So there's an et cetera there. But now, of course, the question becomes, how far down do you have to go? And the answer is, strictly speaking, if you want a Polya tree to accurately reflect an underlying continuous reality, then the tree has to have an infinite number of layers. But of course, we're saved again by the fact that no one ever measures something to infinite accuracy that's conceptually continuous. You would never want to go down any farther than to the point where the size of these little intervals here is smaller than the actual distance between the observations you get by the rounding process, right? So if I round the fish weight to the nearest tenth of a pound, and I got down with one of these things here to where all my partition sets were smaller than a tenth of a pound, then it's too far. I've gone too far. Or at least once I get down to just below that degree of granularity, there's no point in going any farther because you can't learn from the data any lower than that. So in the same way that DPs have that infinite sum that we have to truncate at a finite value, people always truncate Polya trees at a finite number of layers. And people call that number, that integer, capital M. We know from the way that this is set up that the bottom layer, call this integer capital M, choose M finite, popular choice M equals 6, which leads to 2 to the 6th equals 64 partition sets at the bottom. Now, what we're about to do in expressing our uncertainty about the underlying CDF, let's get out of the CDF space again, because no one thinks well in that space. Let's get back to the density space, and let's remember one of our favorite ways of graphically approximating a density, namely a histogram. Polya trees, to capture their uncertainty about the underlying distribution, let's just call it, Polya trees create random histograms. And the effective number of bars in the random histogram is that number right down there, 2 to the capital M. And so you rarely need more than 64 histogram bars to get a pretty good idea what's going on. I guess I've seen problems where people have had to go down to 2 to the 8th, for example, but I don't see people going much lower than that. So now I've told you completely how to specify pi, like it says back here on the PDF. You get to choose these sets, these partition sets, in a way that centers the polytree on any distribution you want. In this case, the standard normal. And so this is done by choosing the cut points on the line which define the partitions. And so this is a little table that shows what I just did. So at level 1, we have those sets B0 and B1, and the cut point is at 0, which is phi inverse of a half. At level 2, we have those 4 sets that I called B00, B01, B10, B11, and the 3 cut points for that are equal to the place that under the normal curve that has a quarter of the area to the left of it, and then the 0, of course, and then the 3/4 place. And now you just keep going. And like it says here at the bottom, page 21, in practice, this process has to stop somewhere. I, in the work I'm going to show you here, use a tree defined down to level m equals 8, which is like working with random histograms, each with 2 to the 8th, which is 256 pins. 64 is often enough, but let's talk about 256. So check it out. Look back at my picture a minute ago. Down at the bottom, there's going to be 256 little histogram bars. They will not be equal width, right? Because look here at this level here, these guys are not equal width because to go from 50% to 25% is not the same as to go from 25% to 0. Obviously, that's infinite, but basically what happens is that the bars close to the middle get narrower, right? Because there's a lot of probability in the standard normal near the middle. So it's a funny-looking histogram because the bars are not equal width. But that's okay, and in fact, you can even do polytrees over again where the bars are of all of equal width. And you simply change the heights of the bars to correspond to what the normal curve would have put in as the heights of those bars as far as its background centering distribution is concerned. But let's stick with these bars here. Then, in effect, uncertainty about the underlying CDF, if we get rid of issues of location and scale and we're just kind of looking at things that are sort of near the normal 0, 1, it comes down to asking the question, how high are each of those 256 bars in that random histogram? And so that's like asking in turn, it's sort of like taking the infinite dimensional capital F and reducing its actual dimensionality down to 256 because we don't need to go any more histogram bars below that. And the thing that makes it a random histogram is that we keep exactly the same bars all the time, but we let the weights, the heights of the histogram bars move up and down in a way that allows it to adapt smoothly to practically any histogram shape you could think of. That's the idea behind a polytree. That makes it sound like what we're really fitting is a parametric model. Remember this, actually, I guess it's this model here, isn't it? At the moment, this model, before I try to put the polytree on it, so let me get back to where I belong. At the moment, this model looks like it has 2 parameters, 1 location, 1 scale, and then however many parameters you need to quantify your uncertainty about capital F. And I started out, if I thought of capital F as infinite, I started out saying, well, that's sort of like an infinite number of parameters, which is something that everyone would agree is pretty hard to learn in a finite amount of time. In fact, strictly speaking, for continuous things, an uncountably infinite number of terms, which is impossible to learn. But now that I've told you that it's a random histogram with 256 bars, it's as though we're replacing our uncertainty for capital F with a vector of 256 parameters that represent the histogram heights that we just don't know, and we're going to try to learn from the data with appropriate amounts of uncertainty around them. So we've turned the problem from a two-parameter problem where we pretended we knew the normal curve to an infinite dimensional problem where we pretend we don't know anything about things except it's centered at the normal curve, down to a problem that looks like it has about 256 plus 2 parameters in it. But actually the news is better than that, because if you think about that histogram down there at the bottom, the height of one of these little bars and the height of the one right next to it should be pretty highly positively correlated with each other, right? Because the histogram is going to be locally smooth. And so if I tell you the height at one place, you've learned quite a bit about the height next to it, 1 bar left of it, 1 bar right of it. And therefore, the effective number of parameters that you're having to estimate in order to get that random histogram is nowhere near 256, because they're all pretty strongly positively correlated with each other as you sweep from left to right. And in practice, I've found that the actual effective number of actual shape parameters of the CDF with 256 bars at the bottom is probably some number on the order of about 20. So it's like having to learn 20 new parameters that all tell you something about the shape of the basic process that's generating data for you. And the difficulty that makes the MCMC take a long time is that, unfortunately, those 256 histogram heights are strongly correlated with the location parameter that you're interested in, because if you change the histogram heights, that changes the mean, right? And so, so the uncertainty we have about the heights of the histogram bars bleeds into or propagates into uncertainty about mu, and that means that the time series trace for mu in the MCMC is going to look like an AR1 with a very high positive autocorrelation. In other words, it's going to have to take a long, long run. In the chapter that I published that I put on the website here, I was finding that I needed Bayesian nonparametric runs in the low millions of iterations to get a good idea what was going on, whereas if I had contented myself with parametric models, I would have needed runs on the order of 100,000. So I'm talking about increases in the length of the run on the order of 10 to 50, for example, to get the Bayesian nonparametric stuff to work with the same Monte Carlo accuracy. Going from 100,000 to, let's say, 5 million is an increase of multiplicative increase of 50, isn't it? Did I do the arithmetic right? So 10 to 50 times longer, and if we have only one CPU, that really does mean 10 to 50 times longer in clock time. But if we have a cluster with thousands of processors, then we can probably kill that 5 or 10 million iterations pretty quickly. So Bayesian nonparametrics, even with pretty big data sets, is doable as long as you can do parallel processing. So, all right. Now I haven't told you about that A sub C, and this is another cool part of the Pauli tree. I'm borrowing this paragraph from my friend Stephen Walker, who wrote a paper about this some years ago. And I haven't figured out any better way to describe it than what they did in this paper, he and his friends. So let me just read this paragraph to you in interpolating my own comments. A helpful image is that of a particle, like a pinball, cascading through the partitions. It starts on the real line and moves into B0 with some probability that we could call C0, or in other words, it moves left with probability C0, or into B1, the right-hand move with probability C1, which is 1 minus C0. In general, on entering a particular partition set, the particle could either move into the left one below it or the right one below it, which would be called B epsilon 0 or B epsilon 1. Let it move into the former with probability C epsilon 0, or into the latter with probability C epsilon 1. If you wanted to fix the standard normal as a way to simulate the draws from this and make the particle move in various places, then all those numbers C0, C1, C00, C01, C10, C11, all those numbers would be known and would be fixed at the right values to get the standard normal curve to come out. But the thing that makes it a random CDF is now we turn those C probabilities of moving left and right, we turn them into draws from beta distributions. We make them random. And that's what makes it turn into a random histogram. Very cool idea. So for Pauli trees, these probabilities, these things, C epsilon, are random beta variables. And at any particular level, when you are at a particular set C, at the set B epsilon, and you're thinking of either moving left with probability C epsilon 0 to the layer below it, or to the right into the set C, the set B epsilon 1. C epsilon 0 is the probability of moving left. C epsilon 1 is the probability of moving right. And we force things so that that pair of numbers is like a draw from a beta distribution. The C epsilon 0 is a draw from a beta distribution with parameters alpha epsilon 0 and alpha epsilon 1. And of course, C epsilon 1 just has to be 1 minus C epsilon 0. And we pick these numbers alpha epsilon 0 and alpha epsilon 1 to be just non-negative numbers. They don't have to be integers. And now collect all those alpha numbers together into a big collection of them. Then a particular Pauli tree distribution is completely specified by the pi and by those things. And so let me draw back over here again. The particle starts here, and it has to begin by deciding whether it wants to fall into the left partition set or the right one. Instead of forcing it to fall to the left with probability 1/2, let's make the probability that it falls in that direction. I used the 1/2 to choose this point here, but now I'm going to forget the 1/2. And I use the 1/4 to choose these points right here. But as soon as I've chosen them, I'm going to forget the 1/4. So I use them to specify the partition cut points. But then once I use them, I forget them. And now, to create a random histogram, I let the probability of moving left and right be draws from the probabilities themselves be random, draws from beta distributions. So I make a draw right here from a beta distribution with probability with parameters alpha 0 and alpha 1. And based on what that number C0 is, I toss a coin and I move left with probability C0, the random beta draw that I got. And then C1, of course, just has to be 1 minus C0. Let's say the particle moved right. Now we're here. Now it has to decide whether to go that way or that way. And I make it go to the left with probability C10 and to the right with probability C11, which is equal to 1 minus C10. And again, I make this a beta draw, but now it's a beta draw with parameters alpha 10 and alpha 11. And so at every level, at level 1, I have to specify these 2 alpha numbers. And at level 2, I have to specify 4 alpha numbers. And at level 3, I have to specify 8 alpha numbers, and so on. Does that make sense? It's always going to be a beta distribution, and the beta always has 2 parameters. And so I call the left-hand one alpha 0 something or other, and the right-hand one alpha 1 something or other. If you collect all those alphas together into a big old set, that together is this thing called script A. Let me try to write the script A in the way that... so the script A is the collection of all the alpha epsilon numbers, all taken together. Now, why does that work, and how does it work? Well, if I wanted to center this distribution at 1/2, I could put in 1 and 1, for example. That would correspond to a uniform distribution, and that would make it have probability 1/2 of going to the left, because a random draw from a uniform has an expectation of 1/2. It would actually move to the left with some probability that varies around 1/2, but that's the point of making the histogram random. You remember what happens to the beta distribution as the parameters get bigger and bigger? For example, what does the beta 10, 10 look like compared with the beta 1, 1? Beta 1, 1 is uniform. What's the beta 10, 10 look like? Anybody remember? It looks a lot like a normal, centered at 1/2, and with not very much spread. In other words, when you take those alphas and you make them bigger, it forces the choices for these probabilities to become smaller. Do you see how that would be? So the bigger you make the alphas, the less uncertainty there is about the value you'll get right here. And in the limit, if you made the alphas all really big, what would come out of this? The C0 would just default to a degenerate 1/2, and this would be degenerate 1/2, and we'd end up with a situation where we would not be sampling from something that's like a normal distribution. We would be sampling from the normal distribution. Does that make sense? If we make the beta parameters really big, then we're going to end up with something that is not very diffuse at all. It's going to be highly peaked. And in the limit for this left-hand one here, if I let the alpha 0 and the alpha 1 both go to infinity, I would get point mass at 1/2, which gets back the normal distribution. So the whole point of making it a random histogram to learn what the actual density is to allow these going left and going right probabilities to vary. And the beta story is a cute trick that makes it work. And we get to load in how big we want the alphas to be. And so look, that's where the prior sample size comes in. We get to load the alphas. The bigger we make the alphas, the more the draw from the polytree prior is going to look like the what? The actual centering distribution that we built the whole thing around. The smaller we make the alphas, the less it's going to look like that. But it will always still be gently disciplined by that distribution. The same way we saw those pictures from the Dirichlet process that looked like raindrops on a hot griddle or water drops on a hot griddle, but they average out to the right thing. The same thing will happen with the polytree. Well, so now that's a lot of alphas to specify, isn't it? Because you've got 2 of them at the top level and 4 here and 8 there, and you get down to level 8, you've got 256 of them to do. No one really wants to specify them all that carefully, and so what people tend to do, it has been shown that to make a polytree choose a continuous distribution with probability 1, the alphas have to grow quickly as the level m of the tree increases. And it turns out that a rate at which m goes up, if you want to make the alphas depend upon m, which you should, and you want to make things get close to continuous distributions with probability 1, I want the alphas to get bigger as m increases. And it turns out that one of the ways you can do that that will achieve the goal of making it choose continuous distributions with probability 1 is to make the alphas go up at a rate which is proportional to m squared. That's just what comes out of the math. And so look, here's the cute trick people do. People take the alpha at level epsilon to be c times m squared, where epsilon defines a set at level m. And in other words, at level 1, I pick a number c, and at level 1, I put in c comma c. At level 2, m is now 2. 2 squared is 4, so I put in 4c, 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 4c. At level 3, m is now 3. M is now 3 squared, which is 9. I put in 9c, 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 all the way across and so on. That makes the alphas grow fast enough so that you guarantee getting a continuous distribution with probability 1 as the number of layers of the polytree gets really big. So the standard thing to do is to pick something like this, and I generally do that. And now we're going to call the resulting object not script A. We'll just call it script A sub c, because m is just defined by whatever level of the tree you're looking at, and c is now a number that represents, hey, look, it represents a prior sample size, doesn't it? Because as we make the number c larger, we're making these beta probabilities degenerate more and more toward point masses at the normal curve, and we move to where a situation where the polytree is going to draw draws that all look very much like the normal curve as c gets bigger. So there we are. There's a polytree. It's done. And as we've seen, C0 is a kind of tuning constant. With small c, the posterior distribution for the CDF of the errors in my model, my location scale model, will be based almost completely on the empirical CDF of those residuals, you could call them. Whereas with large c, the posterior will be based almost completely on the prior centering distribution, which is normal 0, 1. So if you wanted to dummy out Bayesian nonparametrics and make it into Bayesian parametrics centered at the normal distribution, just run a polytree with a huge value of c, and out will come the usual normal result. And then you can start making c get smaller and watch how the results change. And the way they change is telling you how non-normal the data was to begin with without having looked at the data. So that's kind of cool. Oh, and wants to get in? Okay, so a Googler needs to go to the door and let that person in if that's okay. Thank you very much. Now, you've seen why this is called a tree, because there it is. It was a tree, right? A binary tree, in fact. Why is it called a polytree? Well, it's named after George Polya, a wonderful mathematician at Stanford, who unfortunately passed away some years ago. And it's called a polytree because the updating scheme follows something that people call drawing from a Polya-Ern scheme. And so it turns out that the following very cool thing works. If you start out with your model saying that if you knew what capital F was, the yi's would be IID from F, and then you put a polytree prior on F with partition sets capital pi and weights for the, let's call them beta weights A, and now we observe Y1, then here's how you do the poly updating. You go back to your tree, and you start Y1 up here at the top, and you ask, well, does Y1 actually land in the right-hand partition set or the left one? If it lands in the partition set to the right, you add 1 to the alphas over there. If it goes left instead, you add 1 to those alphas. And then you move it down to the next level. And so look what's happening. it's creating something like a pinball tree in which the weights are, every time an observation comes, the weights are all being gently moved toward the way the data actually is. Where the y sub i's fall in each partition set says this is evidence about where the actual data values are, and so you gently move those alpha weights in the direction of what the data is showing you. Isn't that cool? That turns out to be the Polya updating, and that corresponds to a Polya earn scheme. At each level of the tree, if y1 falls into a particular partition set, b epsilon, then 1 is added to the alpha for that set. And so now you know not only how to simulate from a Polya tree prior by coding up the thing I just showed you, but you also know how to simulate from a Polya tree posterior. You start with the prior and you do this Polya earn updating, and that gets you the Polya tree that's the posterior. So by the way, this proves that the Polya tree is another conjugate prior. If you start with a Polya tree as your prior on capital F, then your posterior has to be another Polya tree. And guess what? It's the same Polya tree as it was before in the following senses. It has the same exact pi set, doesn't it? Because the pi set hasn't changed at all. But what happens is that the a's get updated, and they get updated by where the yi's land, and the yi's make the a's update according to this Polya earn scheme. Add 1. You ever heard of a Polya earn scheme, Polya earn sampling? You start with an urn that has some red and some white balls. Take a ball out at random. If it's red, put that ball back in and one other red ball. If it's white, put that white ball back in and another white ball, and keep sampling and see what happens. That's just like what this is, right? Because it says add 1 of the kind you actually got. So it's like adding a red ball when you get a red ball, adding a white ball when you get a white ball. So now I'm ready to show you how it works in terms of code. So back on the course web page, I guess I can kill this off now because we did that already. Sure, let's save them. Back on the course web page, I have written some code for you that samples from both the Polya tree prior and also the Polya tree posterior. So let's go ahead and write this to the desktop. That's not it. Where did it go? Here. Look down here. Let's open it. No, that's not it. That's funny. What's happening is that whenever I project this screen, it ends up, I think what it did is probably wrote the, is there a way to go to the right on these things? Anyway, maybe I'll just grab it like this. I'll see if this works. When you transfer from your own screen to plotting with VGA, the screen gets smaller in order to match the resolution of the device you're working with. Let's try this. I'll grab all that stuff and try putting it in a text file. This sometimes works and sometimes doesn't. Let's find out. Voila. Okay, so I'm going to start a new R to have a fresh start. Why not? And my first reminder to myself is to unbuffer the output so I can watch things happening. So I'm going to unbuffer the output. And then I wrote a function called polya.sim1. This simulates and plots n.simDraws. That's one of its inputs right there. n.simDraws from a Polya tree prior centered at the standard normal distribution with prior sample size C, which is given by this thing called CC again, also often known as alpha. Sometimes people confusingly call the prior sample size in the Dirichlet process, call it alpha, and they do in the Polya tree as well, but I'm going to use the lowercase c. And with the theoretically infinite number of levels of the tree set to the finite value m. So first I wrote a function called polya.sim that does the Polya tree sampling and actually does various plots for us as well. And so let's begin making some draws from the Polya tree prior and see what we get. If I pick a value of c like 0.1, what do you expect the picture to look like? C of 0.1 represents a prior sample size. We're going to be centering things at the standard normal. But C equals 0.1 means we're going to be centering it hardly at all at the standard normal. So what are the individual densities going to look like? real chaotic all over the place, right? Like those water droplets on a hot griddle. Well, in fact, there they are. I've drawn, probably I didn't need to do anywhere near 100 of them for you to see what's going on, but they're just completely chaotic looking, except that the bottom histogram, I averaged all those densities, and the average density is given by the histogram that corresponds to all those average densities is given by the histogram bars, and the average of all those densities is given by the dotted line. And you can see that even with c equals 0.1, on this particular time that I only did it 100 times, even though each one of those draws from the polytree looks nothing like the standard normal curve, when you average over all of them, you get back the standard normal curve, at least to sampling uncertainty. So I just said those things right there. Now let's make C get bigger. If I bump it up to 1, then the result should be that the draws are visibly closer to the centering distribution, and they are. You can see how they're still kind of chaotic looking, but it looks like a kind of a spidery sort of thing around the standard normal distribution. In fact, for the next one, I'm going to use a smaller, I'm going to set C up to 10, but now I'm going to use a smaller number of draws to show you a little bit more of the individual draws. So let's go ahead and do that. And now, practically every draw is practically the same as the standard normal distribution. You'll notice something funny, though. The actual densities all seem to go through the point 0, because they have to, right? Remember how the polytree worked? It was partitioned at that partition set at 0, and then there's going to be another little knot. If you think about splines, they're kind of going to look like splines with knots at the different places that were the cut points for the polytree. All along here, I've been using what for my, I guess I've been using m equals 6 rather than m equals 8. That's fine. That's just fine. You can make that go away if you want. You can use a different choice of partition sets every time you make a draw, as long as you adjust the partition sets appropriately and the heights of the histogram bars with the alphas. So you can take that kind of granularity, which does look kind of funny. You can take that and make it go away by doing a kind of averaging or randomizing process. But it's not a bother to us. Now, let's see about prior to posterior updating. So the following code does two things. It simulates 100 data values from a distribution with a long right-hand tail, and then it samples and plots draws from the polytree posterior that starts with the polytree prior I just showed you, and then updates with the data in step A. And I wrote the function fairly cleanly, except I had to put in a hack. I added an input parameter called y.lim, which controls the vertical height of the plot to make things look better. If I were, again, doing something smarter, I would have been able to do that without having to have the user input it. But hey, let's we all write hacks sometimes, don't we? And let's go ahead and run the code and see how it works. So this takes longer to, okay, good. So let's try running this function with m equals 6. Oh, first I want to show you what the data set looks like. So give you an idea of what we're using as our data. Let's do a histogram of y. There's 100 observations here. And if you say breaks equals 15, I'll try breaks equals 14. You can see that it's a distribution that has a long right-hand tail, but it goes down to -3 and up to +4, for example. And now I'm going to want to start that over again. So par mf row equals c 1, to get it to go back to 1 plotting image instead of 2. Now let's run the function, and let's enter the function and then run it. And I made things in Technicolor. So the red histogram is the data values. The dark blue curve is the standard normal centering distribution. And the dotted lines are draws from the posterior. So what would you have expected with c equals 0.1 and n equals 100? The posterior is a weighted compromise between C votes for the prior distribution, centering distribution, and N votes for the empirical CDF. And so with C equals 0.1 and N equals 100, I should have asked you ahead of time what you would have expected. And what would your answer have been? It should have, the posterior should look a lot like the data set, right? And I should have mentioned to you that these solid lines are draws from the prior, and you can see they're all kind of fluctuating around the blue curve. And the dotted lines are all draws from the posterior. And you can see that they are they're being sharply updated by the data. So the polytree is doing just what we want it to. And the computer just quacked at us for some reason. That's because I wrote quack into the code for some reason. I don't remember why I did that. Now let's try running this function with a bigger value of C. So now, here we go. Now I used a different rescaling. Again, the solid draws are from the prior. The data histogram is always in red. The prior centering distribution is always in blue. And the posterior draws are all in dotted lines. So now with C equals 1 and N equals 100, how do you see things now? You would have expected on intuitive grounds that in comparison with the previous picture, the posterior would be doing what kind of movement? Away from the data and toward the prior, and you see it did. It's now almost halfway between, in fact, the two. But what you're noticing also is that the number C in the polytrees doesn't seem to have a linear effect in a sample size way that it did in DPs in terms of C votes for the centering distribution and N votes for the empirical. It's something that's related to prior sample size, but I can't quantify it directly for you in terms of sample size. Now I ran it over again with C equals 10, and now you see that actually we would have needed to go even farther, wouldn't we have? The prior draws are there. The data draws are trying harder to be draws from the prior than they were before, and I think we could certainly run it again with C equals 50. Let's see what happens then. And now they're practically coincidental. And if I went up to 100, all the draws should be pretty much from the prior. And you can see they are. It ignores the data completely, and the posterior is based completely on the prior, with that same kind of funny business about a knot at 0 and a few knots at other places as well. So this is a machine, like any Bayesian machine. You get to put in information external to the data set. Think about this not as a prior on a parameter vector, but as a prior on the space of all possible sampling distributions. And the prior has two ingredients. It has something that acts like a prior sample size, and it has something that acts like a prior estimate of what the actual sampling distribution is. Is this machinery foolproof, or can it be abused? Will it always give the right answer for any n? If I feed it any data set, will the posterior always concentrate beautifully right on the true data generating process? Of course not. How can I make it break? To get a posterior that's nowhere near the actual data generating process, even if the data set itself was faithfully drawn from the data generating process, how could I make the DP, how could I make either of these BNP priors break? Large value of C combined with a, good or bad choice for F0, combined with a bad choice of F0. So again, no free lunch with any of this stuff. You have to pick the right F0, you have to pick the right C, and if you do that, you get out an answer that has the property that the more data you get for fixed C and fixed F0, the more the posterior moves toward the right answer. I should have shown you that also by showing you data sets that had more and more data with a fixed value of C, and that would have shown you that the posterior was inexorably moving toward the data generating process. Even with a fairly large value of C, the posterior draws would start to move toward the data convincingly as the sample size increased. So that's simple Bayesian nonparametrics. I haven't shown you yet how to do Dirichlet process mixture modeling, where we have uncertainty about the location and scale parameters, for instance, and polyetry mixture modeling, where we have uncertainty about them as well. I will show you those things next week. There's CRAN code. This was all homegrown. I wrote all this code myself, but there's code at CRAN to do actual updating based upon data sets where we are uncertain about more things than I just showed you in this little example. So, okay, good. Let's go back to, did we finish part 1? Yes, we finished, or rather what I called section 1. We finished that. There's probably some more interesting stuff in section 2. And I'm supposed to be stopping again at, okay, 3:45 and then 3:25. That's good. So, returning to this nuclear waste disposal problem, I'll give you an example of the data, and once again, for next time, I'll post this data on the course webpage. We have 10,000 IID sampled values from Mascot, that program that AEA Technologies had written, at what would happen 200 years after you let the underground repository alone, left it alone. And this turns out to be based on a scenario permitting relatively large doses of a nasty compound called strontium-90 occur with relatively low probability. So most of the time, nothing bad happens at all for the people on the Earth's surface, but every now and then you get a really big dose of radioactivity. And the outcome examined is total dose. There turned out to be 3 nuclides, including SR90. In this data set that was arrived at by running their PDE sampler with random inputs and getting random outputs, 9,864, in other words, 98.6% of the 10,000 values were hard zeros in the data. No one got hurt at all. 134 of the other 136 ranged smoothly from 10 to the minus 14th up to 10 to the minus 1. And then the 2 largest values were about 4 and about 189. And 4 is already enough to harm you seriously, and 189 kills you. So every now and then, with low probability, you get a bad dose of radioactivity from this particular scenario. The sample mean came out 0.01964. And the true mean, they have another program called Escort in which they can work out what the true mean is. And it turns out to be about 1 times 10 to the minus 3, which is 21 times smaller than the actual sample mean. And you get a sense of how much effect that outlier had on things. At 1 point out of 10,000, by working out the sample mean omitting the largest observation, it's almost exactly the correct answer. It's about 7 times 10 to the minus 4. The right answer is about 9 times 10 to the minus 4. So there's one observation way out in the right tail that's responsible solely for making this mean much larger than it should be. But that's life in the fast lane. That's how this process runs. You're going to get a really big observation in the right tail every now and then. So I took all the positive dose values and took their logarithms and made a normal QQ plot. And actually, it looks a fair amount like a Gaussian. So if you wanted to do Bayesian nonparametrics here, it would not be a bad idea to center the polyetry or Dirichlet process prior at the log normal, but with unknown mean and variance, and then go from there. Well, let's try first naive frequentist nonparametrics. This distribution fairly closely follows a 2-part or mixture model in which each observation is 0 with probability p and log normal with probability 1 minus p. And I showed you that normal probability plot. So the central limit theorem is actually a nonparametric frequentist method because you get an answer as capital N gets big without having to write down any sampling distribution at all. You get the same answer by the central limit theorem. So we're trying to estimate the population mean. Why not use the sample mean? So let's call the dose values d sub I as I runs from 1 to capital N, and the point estimate theta 1 hat would be d bar, just the mean. And your standard frequentist interval estimate would be based on the hope with such a large capital N that the repeated sampling distribution of theta 1 hat would be close to normal. The central limit theorem is supposed to help here. So your 95% interval estimate would go theta 1 hat plus or minus 1.96 times the standard error, which is the standard deviation of the data values, the dose values, divided by square root of capital N. And this is a non-parametric method because no assumptions about the underlying density that gave rise to this data set are made except that it has finite variance, which is something the central limit theorem needs to know for it to work. And also, I'm not bothered by that because, as I've said to you before, I don't believe in any models that have infinite variance for finite data sets. So, well, let's see how the central limit theorem works. So, if I apply it once to the actual data set, I get 0.01964 as my estimate. And there's the standard deviation, about 1.9. And the 95% interval starts at the mean and goes 1.96 standard errors either way. And it runs down to minus 0.02 and up to plus 0.6. And that does include the true value. But of course, it has done that frequentist thing that's not supposed to happen. It's produced an interval estimate for something that has to be positive, in which the left endpoint has gone negative. Moreover, the largest observation didn't occur in the data set until iteration number 6,132. And if we were to look at all the CLT intervals based on observations 1 through k, as k ran along, we'd find that only 63% of the 195% intervals based on observations in blocks of 100 actually include the truth. So you have to go a long way into the data set until you get intervals that are finally wide enough that include the truth. But they do so by embarrassing themselves by going negative. So the central limit theorem produces silly answers in this problem because the left endpoint of the interval just so often goes negative. Well, to see whether that happens a lot, I regarded the 10,000 dose values at 100 years as a population to be sampled from with replacement. So in effect, I'm bootstrapping the data set to create other data sets that are like what I think I might have seen if I ran that program at AA Technologies longer. And then I repeatedly, 5,000 times, namely, took samples of size little n from this population, again in an IID manner. So here I'm using the bootstrap in a completely different way, not to come up with a single confidence interval, but to test the validity of a method for creating confidence intervals. And I recommend this method to you. If you have a data set and you have a way of creating some inference based upon it, and you're wondering if that inference is well calibrated, bootstrap your data set repeatedly, getting a whole bunch of bootstrap replicates of your data set. Regard each one of them as a pseudo version of a future data set that you would have gotten if you ran the data gathering process for a longer period of time. Run your inferential machinery on each pseudo data set in parallel, and keep track, keep score frequentistly of how often your interval, for instance, includes the right answer. So that's a good way to use the bootstrap for calibration as well as for producing good point and interval estimates. And so here's what we get. I created nominal 95% intervals. With sample size 100, the actual central limit theorem intervals only include the truth 3% of the time. That's even worse than the example I showed you earlier today. With 1,000 observations, it's up to 10% of the time. With 5,000 observations, it's up to 39% of the time. And with 10,000 observations, which is all the observations you got practically, it's in the data set, it's, oops, wow. Didn't want any of that to happen. Looks like I missed a few pages as well, so let me go back for some reason. The mouse tends to jump around on this machine sometimes. In fact, you have to get up to about 50,000 observations, which would have taken such a long time on the supercomputer that AA Technologies was using that you would not be able to afford it. You'd have to have 50,000 observations from that distribution for the central limit theorem to even have its so-called 95% intervals include the truth at least 95% of the time. And for small sample sizes, quote small, like less than or equal to 10,000, the mistakes were always from the interval lying entirely to the left of the truth. And this picture shows what's going on. We can look at the log mean interval length and the coverage rate against the log sample size for these intervals. And you see that the log interval length versus the log sample size should be linear if the sample SD is doing its job properly, because the length of one of these intervals is equal to 1.96 times 2, times Sn over the square root of n. So take the log of both sides, and you find that there should be a linear relationship between log length of the interval and log sample size. But the actual curve does not approximate this straight line. Namely, the actual curve is this one that I'm showing you right here. As my mouse arrow goes along, that's the actual log mean interval length. It doesn't even approach the line until we get up to n to the e to the 10th power, roughly, about e to the 12th power. And e to the 12th is about, actually e to the 10th is about 22,000 observations. Similarly, the actual coverage probability starts out near 0, and it doesn't get up anywhere near proper values until right about when the interval gets long enough. So basically, what's really going on is that the central limit theorem is being betrayed by the sample standard deviation, which, as I showed you before, achieves its approximate unbiasedness on the variance scale by almost always being too small, and then every now and then being much too big. And so that's what's happening here. So that's a rubbish method. And the reason that the method performs so poorly is that even with 7,500 observations going into each average, the distribution of the sample mean is very far from Gaussian because of the extreme skewness of the population. Here's a normal QQ plot of the 5,000 simulated means, each of them based on 7,500 observations, and that's supposed to look like a straight line if we have a normal curve. So 7,500 observations, not enough. 100,000 observations is beginning to get warm, but you still can see that it's not quite normal. It still has appreciable long right-hand tail to it because it's curved in a bowl-shaped upward sort of way. This is a histogram of the 5,000 simulated means in the picture I showed you a minute ago, and you can see that it still has substantial skew. All right, then I tried the bootstrap because that's supposed to be the best non-Bayesian, non-parametric method. And I'd used the percentile method. And as we've seen, this method works okay with large samples from reasonably standard data sets, not too far from Gaussian. But as we've also seen, it can produce poor coverage for small sample sizes and with highly skewed data. And the BCA method, as I've shown you, improves on the percentile method a little bit and is supposed to get better coverage. And it's also non-parametric. It makes no use of information about F apart from having the assumption that its variance is finite. Now, with the actual raw data set, the BCA method yields an interval that runs from about 3 times 10 to the minus 4th up to 0.13. That does include the true mean, and it does also have a nice property. This is how the bootstrap produces answers that are better than the central limit theorem. The BCA intervals can never go negative because they're always sampling from the data, and the data is always strictly positive or 0. So I made an analogous picture to figure 3, and I found that it's still true that only 85% of those nominal 95% intervals include the truth. So every way you want to look at this, the bootstrap still does really badly. In fact, it doesn't do much better. In fact, it pretty well does about as badly as working with the sample mean directly with the 1.96 either way sort of central limit theorem intervals. And in fact, this pretty much reproduces the same table I showed you before, but taking vastly more computer time because the bootstrap takes a lot longer time to do than those simple CLT intervals. So, all right. So the CLT doesn't work. The bootstrap doesn't work in this problem. I tried parametric Bayesian methods by fitting log normal models. And there's some details here that I won't dwell upon for you because I want to get to other topics. And I tried, you can fit it into WinBugs where you work with, it won't quite work with mixture models that have exactly identical mass at a single point, but you can make it be log normal with probability P1 and log normal with a different set of parameters with probability P2. And you replace the zeros in the data set by values of the form epsilon plus or minus tiny log normal noise, and that will correspond to a point mass at mu1 with a very small variance. And so you can trick WinBugs or RJAGs into fitting a model that does work by taking the point mass and making it into something that's a blurry little log normal curve. And so there's some code that shows you how to do it. I don't think I've shown you how to fit mixture models yet, so this code is worth looking at for a minute. I did tell you, I think, that a mixture model corresponds to not knowing for each variable, for each observation, whether it belongs in a particular mixture component or not. And so that means that if we visualize the data set, which here consists of D1, D2, and so on down to D10,000, D capital N, let's keep track of a variable that is an indicator variable for whether this observation comes from mixture component 1 or 2. We have uncertainty about these indicators. Let's call them T1, T2, dot, 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 down to T capital N. But something cool happens. If you know the T's, then you know exactly which component every observation comes from, and that means you have a whole bunch of log normal observations from one group and also a whole bunch of log normal observations from the other group, and you have no trouble estimating the parameters of those distributions. Conversely, if you know the data set plus those parameters, then you can do a pretty good job of estimating which mixture component the observations came from. And so it's perfect for a Gibbs sampler using that ham and eggs thing I told you about the other day. If we had some ham, we could have ham and eggs if we had some eggs. We pretend we know these things here are called latent group indicators, would be a name for them. We pretend temporarily that we know the latent group indicators, and that allows us to estimate the parameters with, given the data. And then we temporarily pretend we know the parameters, and that allows us to better estimate the latent group indicators, and we go around and around in the Gibbs sampler. So it's actually not that hard to do. And the code for doing it is here in this example. I do a loop across all the data values, so 4 I and 1 to n, down like that. And I make a draw from a dcat p open brackets corresponds to making a draw from a categorical distribution that has as many components in it as the length of the vector p. And p is given a Dirichlet distribution with Dirichlet parameter vector alpha. And I just set alpha 1 and alpha 2 both equal to 1, which is like saying p gets a uniform distribution in the prior. We learned from the fact that there's 2 components in alpha that p should be a vector of length 2. And dcat for something that has 2 elements in it is just like tossing a Bernoulli coin with initial probability 1/2 for everybody. And then later on, we're going to learn what those probabilities actually are. And then I make a draw, di, which is a draw from a log normal distribution. And watch this cool trick you can do. You can do double indexing in WinBugs. So observation I comes from a log normal distribution with mean mu of t of I. And so if t of I came out 1 in this first step, then that's the log normal distribution with mean mu 1 and precision tau 1. And if the t of I came out 2 the first time, it's the log normal in the second one with mean mu of 2 and precision tau of 2. So that's a cool way to fit mixture models where you know the number of mixture components. If you don't know how many mixture components there are, it's a harder problem. But if you know the number of mixture components, you can use this trick based on the latent variables to work things out. And there are more examples of this in the WinBugs examples stuff if you want to check it there. They do more mixture modeling than just this simple one. Anyway, I got absurd results. I got an estimate for the thing I care about that came out on the order of 2 times 10 to the plus 7th. And obviously that's absurd. And so when the biggest number in the whole data set was 181, and the reason is that the log normal distribution is unbelievably sensitive to assumptions built into the normal curve about the rate at which the tails fall off. So then I did some modeling with truncated log normal distributions, and that worked quite well. And so I ended up I fit parametric Bayesian models in WinBugs with truncated log normal models, and I got reasonable looking results, which I will skip over and you can read later on. Then I used Bayesian nonparametrics. I built a polyetry prior, and so there's some stuff in here that will imitate what you saw before about how polyetries work. And then I can do inference on the parameters in a Gibbs sampling sort of way. I put down a conjugate prior for those parameters, and I use Gibbs sampling actually I plotted, first of all, to see what's going on, I plotted the conditional likelihood function given particular values of mu and sigma squared. And this is the kind of thing that you get out of Bayesian nonparametric models. We're not used to seeing log likelihood functions that look like that. I think you would agree with me. In all the work we've done so far this quarter, log likelihood functions have been gorgeously smooth. But what happens when you allow in uncertainty about the underlying cumulative distribution function, or they just call it the underlying distribution, is that you can get very jaggedy. This is a conditional likelihood function. You get very jaggedy looking things that have lots of local minima and local maxima. And there's one global maximum here. But if you used a naive method, if you were using maximum likelihood in this model and used a naive method to try to figure out where the maximum was, you would be in serious trouble. If you try to do some kind of empirical Bayes thing with Bayesian nonparametric models, you'd be in really serious trouble. Moreover, the joint conditional log likelihood function for mu and sigma squared with the 100-year data looks like what you get by taking a piece of paper and crumpling it up and then a little bit uncrumpling it. It's the most amazing log likelihood function I've ever seen, conditional on the mu and the sigma squared. So essentially, all of your intuitions about how things are supposed to behave when you've been fitting parametric models all your life, a whole bunch of them fly out the window. You end up with these surfaces, posterior surfaces, that are much rougher than you were expecting because of the uncertainty about the unknown CDF that's underlying the Bayesian nonparametric stuff. So look, this is a contour plot of that same crumpled piece of paper I showed you a minute ago. Have you ever in your life seen a contour plot like that? It looks like something that you would see if you went to some sort of Badlands or something like that. Imagine trying to climb around on that and look around for the highest point. You win $10,000 if you're the first person to the highest point. And you're climbing around locally, and you keep falling into these horrible trenches, right? In between these local peaks, there's these horrible trenches. And so there you go. So basically, I do a kind of give sampling where I first pretend I know what the mu and the sigma squared are. That's just a Pauli update. And then I use a particular kind of metropolis sampling to get the other parameters given F. And there you go. And so we end up with inference for the parameters that we care about, in which these plots have been greatly smoothed just to make them look less frightening to the horses and small children. I smoothed them, except this is one that didn't actually smooth things. The prior is the standard normal here for the CDF capital F of the standardized log values, and the density traces represent samples of draws from the posterior. And so what's happening here is you can see the same kind of compromise happening between the prior and the sample, having chosen a value like c equals 1. But again, you can see amazing lack of smoothness in what we're finding from fitting the data when we don't know what the underlying story is. And so there's some preliminary results here in which shows that the Bayesian nonparametric approach works pretty well. I have another nonparametric case study to show you briefly, but I see that we're at our final break for the day, so let's stop and start again at 4 o'clock. So VC Ops, I'll turn off now and start once again right at 4. Thank you.